We're now at the last section that we do in Calc 3. And we're going to talk about the Stokes theorem. We're going back to the line integral. Work. Okay? So if you have, and this is related to the Green's theorem, but in the Green's theorem it was a flat surface. So now we have a three-dimensional surface. And if you think about it being oriented outward, and you grab a hold of that normal vector and right hand thumb up, so there's the z-axis or the direction of the normal, and you're going around, and you'll, as a result, you get this region in the xy plane that is oriented counterclockwise and is closed. So this is related to the Green's theorem. This is the three-dimensional piece of the Green's theorem. And so if you want to evaluate work, you've got, let S be a oriented surface. So it's a surface with a unit normal vector n, bounded by a piecewise smooth closed curve and with positive orientation. That's that. If F is a vector field whose component function have continuous first partial derivatives on the open region in S and C, then work the integral of F dot dr over the curve in the xy plane down here, this curve, can be evaluated by using the double integral of the surface, okay, curl of F dot n ds. That is the Stokes theorem. The Stokes theorem, related to the Green's theorem. Use the Stokes theorem to evaluate this integral. We've got 2x plus 2y plus z equals 6, that same plane we had earlier. We have a unit normal vector coming out, okay? So out of the plane, oriented. So we have our path, our curve is oriented there. Here's our curve. Okay. Very difficult integral to do that way over the vector field minus y squared I z j plus xk. But we can use the Stokes theorem to evaluate this. And remember that NDS is minus the partial derivative of x I minus partial derivative of y j plus k dA. So if we take our curve, our path here, z is our g of x, is 6 minus 2x minus 2y. The curl of this function, I, j, k, partial derivative of x, y, and z, of y minus y squared z x. So it's going to be I, the derivative of y in relationship to x, which is 0, minus the derivative of z in relation to z, so we've got minus I, minus j, partial derivative of x in relationship to x is 1, partial derivative of z in relationship to minus y squared is 0, so we have minus j, and then the partial derivative of x in relation to z is 0, partial derivative of y in relationship to minus y squared is minus 2y, so it becomes plus 2y, k. So we have the curl, minus I, minus j, plus 2yk, dot with n ds. Well, the derivative of this in relation to x is minus 1, so, sorry, minus 2. So minus and minus 2 is 2i. Derivative of this ratio to y is minus 2. So the derivative is going to be positive 2j. And the derivative of z is going to be plus k dA. Where A is our region down here in the xy plane. So if we go dx dy, it's easy to see that x is going from 0 to 3. So 0 to 3. This is a line. So y is going from 0 out to that line, and that line is going to be, because we're doing x first, solve it for x, 3 minus y, and it becomes a fairly easy integral to evaluate. Okay. to evaluate. Then they say try evaluating it without that, and I'm not going to go through it all, but one way to do it is you'd have to get all the curves parametrically, piecewise smooth curve, and then we'd have to do 3 integrals to get there, get the same result. Stokes' theorem makes things a whole lot easier. The Stokes theorem. Again, in verifying the Stokes theorem, we've got z equals 4x squared minus y squared, parabola, okay? And we have the circle down in the xy plane working. The vector value function 2z x y squared, one we just did a moment ago, so we related to it a moment ago. So derivative of y equals y squared is 2y, so we get 2yi, and then you get minus 2, but minus 2, so plus 2, and then you get 1. So we get the curl is that, so the curl dot with n dot s, so here's our z equals, so the derivative in relationship to x is minus 2x, relationship to y is minus 2y, so minus g, so it becomes 2xi minus y, 2yj plus k dA. A is our circle, going from minus the square root to the square root, minus 2 to 2, dy dx, and we end up with 4 pi. Okay? That's using the Stokes theorem. Okay? As a line integral, we can use this result, and you'll see when they go through it, this becomes a little bit more difficult because we have to take the curve and make it a parametric curve, use sine and cosine, and do the things there, and retain partial derivatives, the curl again to get to here, and we get the same result. But the Stokes theorem does make things somewhat easier. The Stokes theorem does make things somewhat easier. It's interesting, again, that this Stokes theorem takes a line integral and relates it to a surface integral. It takes a line integral, work, and relates it to a surface integral. And part of the concept is 3-dimensional whirlpool, liquid flowing in that direction. Here's our vector field that does that. Okay? Since it's only on the surface here, it's just x and y. So using the integral, the curl n ds, here's the curl. You'll end up here. And the s, okay? So we get 3, the square root of x squared minus y squared, n ds. Well, the unit normal vector is just the k vector. There it is, just k. So it's going to be n ds is going to be 1 dA, and we can come up with the result. Okay? Right? So this is the work done in doing the whirlpool, the work done. So again, this chapter can be summed up using charts. Right? And this chart, the fundamental theorem of line integrals, one way to evaluate a line integral. Stokes' theorem, another way to evaluate a line integral. And Green's theorem, another way to evaluate a line integral. Okay? And then the divergence theorem, a way to evaluate a surface integral. This chart, along with the chart earlier in the chapter, and section 1, dealing with conservative vector fields, is what's in chapter 15.